Okay, so this is the outline of chapter 30. So first of all, we will introduce the Faraday's law and Lenz's law. Okay, and then we'll introduce induction and energy transfer. And then induce E field. Okay, so all this stuff are related to the Faraday's law. Okay, you just try to mention, okay, how the energy is transferred and what is the induced E field, what is so-called the induced electromotive force, EMF. And then we'll talk about the circuit element called inductor and its inductance. Okay, we'll talk about self-inductance. Self-inductance is actually the phenomenon of an inductor. And then the RL circuit, we will just slightly introduce it. I cannot show the proof at this moment because I assume you don't know how to solve a linear ODE yet. So after this chapter, I will have some supplementary math, okay, mentioning about how to solve a linear constant coefficient ODE. And then we'll also talk about this energy stored in a B field and energy density in a B field. And finally, we have a mutual induction. You can consider as a transformer, okay, 变压器, okay. So which means that if we have two coils placing close together, so we can generate B field from one coil, and then it can, if this B field is changing, then the magnetic flux over the second coil may also changing, and this time varying magnetic flux, according to Faraday's law, will generate an induced EMF. Okay, so this is the energy transfer from one coil to another. So we usually call it a transformer. Okay, so this is the Faraday's law and Lenz's law. Okay, so here we take a look at this first experiment. Okay, so it says that conducting loop is connected to a sensitive ammeter. Okay, so here sensitive. Okay, no back. Okay, so sensitive means it can send some small value. Okay, so ammeter means this is a meter to measure the current. Okay, the meter to measure the current. We also have voltmeter to measure the voltage, or you can consider this a potential difference. Okay, we have voltmeter and also ammeter. Ammeter is used to measure current. Okay, so a sensitive ammeter means it can measure some small current. Okay, so which means that this statement is actually referred to this part. Okay, we have a conducting loop. And then connecting to, this is actually the ammeter. Okay, and because there is no battery or no other source of EMF induced, there is no current. Okay, so at the very beginning, just try to ignore this part. So up till now, it only mentioned that we have this part only. And as much as there is no battery connecting to the loop, there will be no potential difference, no current at all. However, if we try to move a bar magnet toward the loop, a current suddenly appears in this current. Okay, the current disappear when the magnet stops moving. Okay, so for the third step, we try to consider this magnet bar. Okay, at the beginning, this magnet bar is far away from this loop, and then we try to moving it closer and closer to this loop. And something we need to pay attention is that we need to consider the direction. Okay, so this is the loop, and then we try to put this bar. Okay, this maybe a north face, is moving towards this loop. Okay, something like this direction. Okay, if you just try to move it from this direction like this, then yeah, there won't be any current. But actually it says if we try to move this magnet bar close to this loop, then there will be a sudden current appears. Okay, and the current disappear when the magnet stop moving. Okay, so this is also very important. Okay, so after we put this magnet bar here, and then we don't actually move the magnet bar, then there will be no current again. Okay, so the current does not due to the B field. Okay, does not due to the B field itself. Okay, at the very beginning, the magnet bar is very far away, then there will be no B field. And we try to put this bar closer and closer, and there will be a current. But after we placing the magnet bar near it, and then we don't move the magnet bar at all, then there will be no current again. Okay, if we then move this magnet away, a current again suddenly appear, but now in the opposite direction. So we move it back, okay, move it away in the reverse direction. So in this case, the current suddenly appear again, yeah, but the current in the opposite direction. So it's an observation. So try to remember some of these details here. So yeah, so this is the first experiment. Okay, so here it says if we experiment for a while, we would discover the following facts. Okay, so a current appear only if there is a relative motion. Okay, relative motion is 相对运动啊，相对运动。所以意思是说，一开始的话就是这个线圈不动，这个magnet bar 移过来的时候，它会有电流，就是在动的时候它会有电流，或者是如果两个一起动，它就不会有，或者是如果你 magnet bar 不动，但是你的圈移走或者移过来的话，也可以。相对运动的话，就是它们之间的相互的位置有改变，这是 relative motion between the loop and the magnet bar. Okay, the current disappear when the relative motion between them cease. Okay, 就是没有相对运动的时候就没有电流。Okay, so and then there are some smaller point. Okay, so it says the first one is a faster motion of the magnet produces a greater current. Okay, so it's related to the speed. Okay, to the speed of the motion. Okay, to the speed of the motion. And then second, if moving the magnet's north pole towards the loop causes, say, clockwise current, then moving the north pole away causes counterclockwise current. Okay. Actually, this is just as what the previous page says. And here, moving the south pole towards or away from the loop also causes current, but in reverse direction from the north pole effects. Okay, so which means that which pole of the magnet we are facing this coil is actually important. Okay, if we move this north pole from far away to the loop, it will generate a current. Let's say clockwise. Then we move this north pole away, then it will be counterclockwise. If we just make it like this is S, this is N. Okay, moving it close to the loop, then it will generate counterclockwise current, and moving it away will generate clockwise current. So it is related to whether it's a north pole or south pole. Okay, so this is some more observation. Okay, so here we have another experiment set up. Okay, so second experiment. So for this experiment, we use the apparatus. Apparatus 就是装置. Okay, so with the two conducting loop close to each other but not touching. Okay. 上一个的话这个是一个 magnet bar， 那现在的话我们把它转换成这个 这个是一个线圈啊。This is a loop, and then this is a switch. This is a resistor. This is a battery. Okay, so in such a way, if the switch is open, then there will be no current. But if the switch is closed, then there will be current. So which means that we can use this switch to control whether there are current going through this this loop. Okay, to replace the magnet bar. Okay, so in the previous chapter, we already know that current coil is equivalent to a magnet bar. So which means that if it is closed, then it means that there is a magnet bar there. And if it is open, then there is no current. Then there is nothing. There's nothing. Or it will not generate B field. Okay. So in such a way, for this experiment, and then if we close switch S to turn on a current in the right-hand loop, the meter suddenly and briefly register a current. Okay, so it says originally the switch is open. Then if we close the switch, which means that there will be a current appear. Okay, so this loop will suddenly generate some B field going through this loop. Okay, and there will be a sudden current. Okay, briefly register a current in the left-hand loop. And if the switch remain closed, which means that we still have this magnetic dipole. Okay, magnetic dipole current carrying loop there. No further current. Just like if we just place the magnet bar near the loop without moving, okay, there's no current. Okay, and then if we then open the switch, another sudden current, another sudden and brief induced current appear in the left-hand loop, but in the opposite direction, similar to we try to move this magnet bar away. Okay, so we can get an induced current only when the current in the right-hand loop is changing. Okay, changing is the most important factor here, or either turning on or turning off, just like we try to move a magnet bar close to the loop or moving away from the loop. Okay, and not when it is constant. Okay, 它不动的时候就不会有。Okay, and then the induced EMF and induced current in this experiment are apparently caused when something changes. But what is that something? Okay, Faraday news. Okay, maybe I have not mentioned what is an EMF yet. Okay, so an EMF in long term is electromotive force. Okay, electromotive force. Okay, we just use the EMF here, so the short form is EMF, electromotive force. You can somehow consider it similar to a potential difference. Okay, but not quite the same. Yeah, but yeah, simply speaking, it is similar to a potential difference, and you try to understand it as a potential difference at the beginning is okay, I think. Okay, so you consider it something like potential difference or voltage. Okay, induced voltage along with this induced current for a loop. Okay, so next Faraday's knew why or what is actually this phenomenon. Okay, so here is the Faraday's of induction. So he realized that an EMF and a current can be induced in a loop, as in our two experiments, by changing the amount of B field passed through the loop. Okay, so he further realized that the amount of B field can be visualized in terms of magnetic field lines passing through the loop, and the magnetic flux through an area A in a magnetic field or B field is actually defined as this one, So we try to integrate that's B field BDA, okay, integrating BDA. So that's why at the beginning of chapter 28 I say a rigorous name for the B field is not magnetic field, it should be the magnetic flux density. Magnetic flux density, because if we try to integrating it along an area, okay, it becomes the magnetic flux. So it's something like the magnetic flux density rather than a magnetic field. Okay. So here is a magnetic flux, something similar to the electric flux when we learn the electric flux in chapter 23. Okay, but here we don't need a closed surface and never be a closed surface. This surface is actually enclosed by the coil. Okay, something like this. This area is enclosed by a loop. Okay. So where the integral is taking over the area, and the SI unit of magnetic flux is Weber. Okay, the SI unit of magnetic flux is Weber, and then the short form is WB. Okay, so the 1 WB is actually T times meter square, because Tesla is the SI unit of the B field. Okay, so you can clearly see that this is Tesla, this is meter square. Okay, so this one should have SI unit of Tesla times meter square, which is defined to be Weber. And if B is perpendicular to the area and is uniform over it, then this surface integral is simplified to a product. Okay, the B field is uniform multiplied by the cross-section area. So nothing but phi B equals B times A. Okay, so here it says the magnetic field, the magnitude of the EMF, induced in a conducting loop is equal to the rate at which the B field, the magnetic flux of phi B through the loop changes with time. Okay, so here is the Faraday's law. Okay, the formula is simply like that. This is the induced EMF equals the negative of the derivative of the magnetic flux with respect to time. And if the coil has n turns, we just multiply it by n, by the number of turns. Okay, so this is actually a form of the Faraday's law. Okay, so this induced EMF is actually this derivative, but we take a negative side. Of course, later we will write a complete form of the Faraday's law. We will write this EMF as a line integral, but some pages later. Okay, but so up till now we can know this Faraday's law has a form like this or that. Okay, depends on whether it has one turn or multiple turns. Okay, so the induced EMF tends to opposite the flux change, and the minus sign indicates this opposition. This minus sign is referred to as Lenz's law. Okay, Lenz's law 的意思就是在法拉第定律 Faraday's law 里面，这个负号就叫做Lenz's law。Lenz's law. OK， 它的原因是为什么一个负号它就可以叫做一个定律了？因为 你要理解它的话，还不是那么简单，因为它就是一个 derivative 啊，它是一个导数啊，它是一个导数，所以你要了解这个负号的意义，还不是一个静止的状态，它是一个动态的，所以它就称为一个定律。Okay, so let's see. Okay, before seeing what is a Lenz's law, so we have a sample problem first. So here it says the long solenoid S has 220 turns per centimeter. So this is somehow like a number of turns per unit length, a small n. Yeah, but not the SI unit. So we still need to change it into SI unit. And carry a current I is diameter D. Okay. At its center, we place 130 turn closely packed coil C of the diameter D. The current in the solenoid is reduced to 0 at a steady rate in 25 milliseconds. What is the magnitude of the EMF that is induced in a coil C while the current in the solenoid is changing? 所以这个的话，就跟你们做实验的时候有点类似，但是又不完全一样。这个是一个电流，它会以一个均匀的倍率去改变。那到时候的话是给一个直流电不是，是给一个交流电，就是一个正弦波。那所以有点不一样，但是大致上是一个大的，它会产生一些 B field， 然后放一个小的线圈进去感应去 induce 是感应嘛，感应那个磁场的改变。Okay, so here we have a big coil S. We have some current. So at the beginning is 1.5 A and then it is reduced. This current is actually reduced to 0 at a steady rate. OK， 以一个均匀的速率去减少的，就是一开始是 1.5 A， 然后在25 millisecond 的时候减到0，然后直线的减少。OK, so so first of all we try to calculate phi b because we can use Faraday's law to find the EMF generate in this coil C. But before that, we need to find the magnetic flux, and then we can try to find the derivative of it so that we can know the EMF using the Faraday's law. Okay, so phi b is actually B times A, so which is mu 0 I n. Okay, so this is an expression from the last chapter. So mu 0 I n and then times capital A is the cross-section area. Okay, so mu 0 is actually 4 pi times 10 to negative 7. And then we have I. I is 1.5 and then times n. N. Okay, this is 220 turns per centimeter. But the SI unit should be meter. Okay, so we need to make it to meter, but we need to multiply it by 100. Yeah, because this is per centimeter, is in the denominator. Okay, so making it meter, we need to multiply 100 in the numerator so that the value doesn't change. So 220 times 100 is 22,000. And then it's the cross-section area of coil C. This is A. This is A. This is A. Okay, so A is actually pi r squared. So the closely packed coil C of diameter D. So diameter, change it to radius. We should divide by 2. Okay, so this is 0.021. Okay, and then divide by 2 and then take the square. Okay, and this one is actually 1.44 times 10 to the negative 5th Weber. So this is the magnetic flux for the coil C at the beginning. And at 25 milliseconds, this magnetic flux will be 0 because there will be no current at 25 milliseconds. So in such a way, you can consider something like this is phi B at 0 second, and then for 25 milliseconds, it reduced to 0. Okay, so and then we need to consider the derivative. Okay, so using the actually the derivative between 0 and 25 milliseconds will be d phi b dt should be negative. Should be negative 1.44 times 10 to negative 5th power, and then divided by 25 milliseconds. 25 times 10 to negative 3rd. Okay, so this is actually negative 5.76 times 10 to negative 4 Weber per second. Okay. So because at the 0 second, okay, this is phi B, which is this value, and at 25 milliseconds, the current becomes 0. And also we know that the phi B generate the phi B should be proportional to the current. The phi B is actually proportional to the current. Okay, so if the current is reduced in a static rate, so the phi B also reduced in a static rate. So this the slope of this curve is actually this one. Okay, so next, after we know the derivative of the B field with respect to time, we can have E equals negative m d phi b dt, okay, which is the Faraday's law. So we just need to plug in a number. Okay, we know there are 130 turns for the coil C, so we have 130 times 5.76 times 10 to negative 4. Okay, so this is a negative sign, this is another negative sign, so this is a positive number. Okay, so finally it is a 75 millivolt. Not quite large, but yeah, it is measurable. So actually this is the magnitude of the EMF that's induced in a coil C, while the current is in the solenoid is changing. Okay. Okay, so after having a sample problem to get some idea how to what does it mean by the induced EMF or induced current. Okay, so here we try to explain the Lenz's law. How do we use it to determine the direction of the EMF? Okay. So here it says an induced current has a direction such that the B field due to this induced current opposites the change in the magnetic flux that induces the current. Okay, 所以是跟改变的方向相反，它不是跟 B field 的方向相反，它是跟 B field 或者是 magnetic flux 改变的方向相反。OK， 什么意思？那 the induced EMF has the same direction as the induced current， 就跟它同一个方向。然后and then Lenz's law at work. Okay, so as the magnet is moved towards the loop, a current is induced in the loop, and the current produced its own B field with magnetic dipole moment oriented so that opposite the motion of the magnet. Thus, the induced current must be counterclockwise as shown. Okay, so what does it mean? Oh, very, very lengthy. Okay, it actually means that if we have a magnet bar very, very far away, then there will be no B field or no magnetic flux going through this this coil. Okay, so if we try to move this bar, okay, let's say from top to bottom, okay, moving close to it, then actually this so the magnetic field generated by this magnetic bar should be something like this, pointing downward, and actually it will be stronger and stronger because this B field, if it is closer to the bar, should be stronger. Okay, so if we try to move this bar closer to the loop, the magnetic flux pointing downward is actually increasing. So in such a way, this loop will try to generate some B field that is pointing upward. Okay, because this B field is pointing downward and increasing. So this generated B field by this loop should be pointing upward to cancel this change. Of course, it tries to cancel part of it, not all. So after canceling some, then there will still be some B field remains. But actually, it will make the induced B field pointing upward, and in such a way, this current should be in this direction. Okay, you can use a right hand rule. Your finger pointing to the top, your four fingers is somehow like counterclockwise. Okay, so here we have a more complicated figure. Okay, so there are actually four cases. There are actually four cases, so that you can understand it clearly. So first of all, if we have the induced current create this field, try to offset the change. Okay, so here increase the external B field, induce a current with a field B induced that opposite the change. Okay, so actually, originally we assume that we have a B field, which is the external, which is generated externally. 就是外面有一个什么东西，它产生一个电场 B， 是外面产生的，跟这个圈无关。然后这个 B field 是在增强的，而且是指向下面。Okay, pointing downward and increasing B field. Okay, so in such a way, if this B field is pointing downward and increasing, okay, the magnetic flux pointing downward is also increasing. Okay, so this loop will try to generate a B field which is pointing upward. Okay, so which means that if this loop want to generate B induced pointing upward, this current is somehow like counterclockwise. Okay, so like this direction. Okay, so this is the first case. And then for the second case, this B field is still pointing downward, but here the B field is actually increasing. So it's actually decreasing. So decreasing the external field B induce a current with a field B induced that opposite the change, still opposite the change. But you can see here, this phi B is still pointing downward because B is pointing downward. But this phi B is decreasing. Okay, so the change is like, we have something pointing upward. Okay, canceling part of this B. Okay, so the B induced this time will be pointing downward to cancel this change. So in this way, B induced is pointing downward. Okay, and still using the right hand rule, you can see that the I should be like clockwise, okay, to generate this B induced. So this is actually the second case. So this is phi B pointing downward and increasing. This is phi B pointing downward and increasing. Okay, so for the third case, here we have the increasing the external B field. So this time, this B field is actually pointing upward. Okay, so this phi B is actually pointing upward, and this B field is increasing. So this B field pointing upward is increasing. So still a field B induced that opposite the change. Okay, all the way opposite the change. Okay, but as much as phi B is pointing upward and increasing, so if this B induced try to opposite the change, this B induced should be pointing downward. And still similar to this one, the I should be like clockwise to generate this B induced. Okay, so this is actually the third case, and finally the fourth case. If B, the external field B is decreasing, so phi B is pointing upward and is decreasing. So still a field B induced that opposites the change. Okay, so in such a way, the phi B is pointing upward and decreasing. In order to oppose this change, this B induced should be pointing upward. Okay, and using the right hand rule, you use your thumb pointing upward, your forefinger is in this direction, is counterclockwise. Okay, so this is all the four cases. Okay, so it not only related to the B field direction, but also how does it change? So it's just like they are multiplying together. So simply speaking, it turns out to be this elegant formula. Okay, so it's somehow like this negative sign means it is opposite to the change, and and then the sign of this derivative is actually like how does it change? Okay, whether it's increasing or decreasing, increasing or decreasing, or originally whether it is positive or negative. Okay, so this derivative already include all the cases in it, so it's a very elegant expression. Okay, and then it turns out to be the Lenz's law. And then the Lenz's law is like the negative sign of the Faraday's law. And yeah, in my opinion, it also includes the derivative, the sign of the derivative. But it doesn't really matter. Actually, finally, what we actually use is the Faraday's law. And sometimes we still need to use this Lenz's law to determine whether the induced EMF is like clockwise or counterclockwise. So we still need to use it to determine the direction of the induced current, induced EMF. Okay, so here we have a sample problem so that we can try to practice about this Faraday's law and the Lenz's law. Okay, so it says a conducting loop consisting of a half circle of a radius r and 3 strict sections. Okay, so this is a semicircle, this is one strict section, and then a second one, and the third strict section. So the half circle lies in the uniform magnetic field that is directly out of the page. Okay, so assume above the dotted line we have a uniform B field. Indicate by this green dot. Okay, the B field is actually pointing out of the page. Okay, so the field magnitude is given by this B equals 4t squared plus 2t plus 3. Okay, so this is related to the time. So with B in Tesla and T in second. Okay, so in ideal battery, with EMF E bat to be 2 volt and is connected to the loop. Okay, so this is the E bat. Okay, which is 2 volt, Okay, an ideal battery with EMF E. Okay, so the resistance of the loop is 2 ohm for this whole loop. Okay, it asks what is the magnitude and direction of the EMF E induced around the loop by the field at t equals 10 seconds. Okay, so actually we can try to find the E induced. Okay, so here we just try to take the absolute value. Okay, we can try to determine the direction later using the Lenz's law independently. So here we just try to take the derivative of the phi b of with respect to time, so that we have the induced EMF, Okay, so here we only have a single term, so capital N equals 1 here. So we only have this derivative. So actually this d dt, the phi b is actually b times A. And actually A is a constant. The A doesn't change at all. So A is a constant. We can move it to the front. So we only have a dB dt. And actually we can see that B is a function of time, so that we can take the derivative. And here A is a semicircle, so it is actually pi r squared over 2 for a semicircle. And then we have a d dt, and then we put in the expression of B here, which is a 4t squared plus 2t plus 3. Okay, so taking derivative is really easy. So we have a pi r squared over 2, and then the derivative of 4t squared should be 8t, and then the derivative of 2t squared should be 2, and then the derivative of 3 is a 0. Okay, so nothing special. Okay, so here we would like to find the magnitude of the E induced at t equals 10 seconds. So here we just substitute t equals 10 seconds here. And then we can just plug in all the values. Pi r squared, r is 0.2 meter. So 0.2 square over 2, and then multiply by 8t. 8 times 10 seconds is 8 times 10 plus 2. So this value is 5.2 volt, which is quite large. And actually, we now need to determine the direction of this EMF. Okay, so actually we can see that this B field is pointing out of the page. So we consider this positive value means out of the page. And we can see that when t is larger than 0, this thing is actually like increasing. Yeah, we have a square, we have a t. Okay, so we can simply imagine that this is increasing. B is actually increasing when t is positive. Okay, so which means that the B is pointing out of the page and also increasing. So which means that B induced should be pointing into the page. Okay, B induced should be pointing into the page. Okay, so here we can use the right-hand rule to determine the the direction of the induced current or the direction of the EMF. So you use your thumb pointing into the page. your finger should be like clockwise. Okay, so we know that this is the direction of the I induced and also the EMF. The EMF is in this direction. Okay, so the induced current is actually clockwise. It's actually clockwise. Okay, so next, it asks you what is the current? What is the current in the loop at t equals 10 seconds? Okay, so just now we already know that this is the direction of the EMF. This is the direction of the EMF. Of course, we should use the Ohm's law to determine the current. Yeah. Here we have the E battery, and also we have this EMF. Let's say this is E induced. E induced at t equals 10 seconds. Okay, we already know that E induced at t equals 10 seconds should be 5.2 volt. We already know that. So in such a way, the I should be E net. Okay, the net electromotive force divided by the resistance. Yeah, we already know the resistance to be 2 ohms, so nothing special. But actually, what is E net? E net should be like E induced minus E bat. That's why I said electromotive force is something like a potential difference. Actually, here is a battery. It is like a potential difference. Okay, and then this EMF can be subtracted from this E battery. So I say you can somehow consider it as a potential difference, and then they can be subtracted from each other. Okay, so here we try to substitute the number 5.2 minus 2 over 2. So this is actually 1.6 ampere. Okay, why it is subtract from each other? Okay, the EMF, the induced EMF is actually clockwise. It's actually clockwise, according to what I mentioned in the previous page. And actually, E battery, this is a positive side. This is a negative side, which means that if we don't consider the EMF, the current generated by this E battery should be in that direction. Okay, so they are in opposite direction. So they should have opposite signs. Okay, which means that we should either subtract E induced by E battery or subtract E battery by E induced. But the absolute value, we can see that E induced is 5.2. That one is 2 volt. This one is smaller. So we try to subtract E induced by E battery. And then finally, the current also follows the direction of this EMF. Okay, so actually the EMF is still a little bit different from a potential difference. Actually, for the battery, you can consider it like if it is an E battery, you can consider this is 0 volt on the left side, and this is 2 volt on the right side. Okay, it's like on the left side 0 is 2 volt, but this EMF, this EMF is like it is distributed from this part to there. So it means that this 5.2 volt is somehow like consider it like still it is 2 volt. So it is like we have all the way 2 volt at this point. So finally, it is somehow like there is a 2 volt plus 5.2 volt there. So that it is like a 2 volt and then increase gradually, and then all the way up to this is 2 volt plus 5.2 volt here. And then it tends to have has a current going like this. Or I should say this is, is not something like that. Yeah, there should be something like this is a 0 volt, and then there is a EMF going lower and lower, and then all the way up to here, and then there is a 2 volt actually inside it, and then it leads to a current, something like going clockwise. Okay, so let's end here today, and then I'll see you next week.